Hello everyone. So, till now we have learned finite difference method and applied this technique to discretize steady and unsteady diffusion equation, convective diffusive equation. We also solved vorticity stream function equations and Navier-Stokes equations using finite difference method. However, there are some limitations in using finite difference method. Firstly, it uses orthogonal Cartesian grid, and secondly, the discretization may not necessarily be conservative. So, to overcome this problem, we can use finite volume method to discretize the governing equations. In finite volume method, the solution domain is subdivided into a finite number of small non-overlapping control volumes by a grid. Finite volume method uses integral form of the governing equations and it inherently conserves the basic conservation of governing variables. Although finite volume method can be extended to complex geometry where we can have arbitrary control volumes. In today's lecture, however, we will use only Cartesian orthogonal grid. So, to start with, first let us discuss about the terminology used in finite volume method. First, we will consider the grid in a 2-dimensional domain, then in 3-dimensional domain. So, you can see, so this is just grid in 2 dimensions, this is the x direction and this is your y direction. So, you can see these are orthogonal grid. In finite volume method, so we consider the main contour volume as this one and denoted by P, and the center of this main control volume is known as cell center. So, this is your main control volume and it is denoted as P. Okay, the cell center of this main control volume is denoted by P. So, this is your cell center. So, this is your cell center. So, you can see this is the volume, main control volume. So, for this particular case we have 4 faces. Okay. So, this is one face, this is one face, this is one face, this is one face. So, this is your quadrilateral grid. So, in 2 dimension we have 4 faces and the center of each face is known as face center. So, you can see this is your one face center and this is denoted as small e. So, this is your faces, okay, and this is your face center. So, we can see that in 2D if we consider quadrilateral grid, then in the main control volume we have 4 faces and in each face we have the face center. So, 4 face center we have and we have also 4 neighbors. Okay. So, the main control volume cell center is P and its neighbor are denoted as capital E, which is actually in the right direction, capital N in the north side, capital W which is your west side and capital S which is your south side. So, east, west, north and south, these are the 4 neighbored cells. So, these are known as neighbored cells. Neighbor cell. Okay. In 2D as we have 4 faces, so we will have 4 neighbor cells and we can have this phase center small e we have denoted as it is in east side, as it is in east side, small n in north side, small w which is the phase center of the west phase, and small s is the phase center of south phase. You can see that the main control volume, okay, of size delta x into delta y. So, you can see that we have the volume of this P cell is delta x into delta y, and the distance between the neighbor cell center and the main control volume center are denoted as small delta y. So, capital N and capital P, small delta y north side, and P and S, this distance is denoted as delta y small s. Similarly, capital P and capital W, this distance is denoted as delta x small w, and the distance between capital E and capital P, this distance is denoted as delta x small e. So, these are actually the distance between two cell centers, two neighbor cell centers. And now we have 4 phases and it will have the surface vector. In finite volume method, we always use the normal which is outside the control volume, that is considered as positive. So, in this particular case you can see the phase normal always denoted as positive which is outward. Okay. So, this is your positive. Okay. So, this is phase normal, this is your phase normal. So, this is, you can see now it is negative x direction. Okay. So, you can see this normal phase normal, this phase normal is negative to x direction and this phase normal is negative to y direction. Okay. But always we consider the phase normal as outward direction from the main control volume. Now, let us calculate the surface area vector of each phase. So, for this E you can see that SE in 2 dimension case, obviously it is the absolute surface area of east phase AE into the unit vector in x direction, that is your I. So, you can see the AE is the magnitude of this east phase and it is nothing but delta y, because you can see this is your delta y. So, it will be delta y I. Similarly, now if you see north phase, then you can write S north is equal to A north. So, n is the magnitude of this surface vector and in which direction, in y direction unit vector is j. So, it will be, you can see the area of this phase north phase is delta x. So, this is your delta x j. Now, if you consider west and south phase, then the phase normal is negative to x and y direction respectively. So, we will write S w which is your west surface vector, that is your minus A w I. So, this minus sign is coming as your phase normal is negative to x direction. Okay. So, it will be minus delta y I. Similarly, A south you can write as A south. Okay. So, j, so it will be negative because this surface normal is negative to y direction. So, it will be, so this is your delta x. So, it will be minus delta x into j, and volume of the main cell is delta x into delta y. Now, if you consider the grid in 3 dimension, so you can consider the z direction, and in z direction the unit vector is k, and similarly you can write. So, you can see this is the main control volume P. Okay. So, this is your x direction, this is your y direction, and this is your z direction. So, your in x direction, so it is small e east phase, this is your small w west phase center. In y direction this is your north, so this is your north phase center, this is your south phase center, and in z direction, so this is your top, so top phase center and B for bottom phase center. So obviously in bottom you can see the phase normal will be negative to z direction, and the main cell is having the dimensions of delta x, delta y and delta z. So you can write the volume of the main cell is delta x into delta y into delta z. Okay. And similarly we can calculate the surface area vector of each phase. So SE it will be AE into I, okay. And now east face if you see, so this is your east face, the front face is your east face, okay, front face is east face. So what is the magnitude of the surface area? That is your delta y into delta z, okay, because this is your delta y distance and this is your delta z. So it will be delta y into delta z into I, okay. So AE is nothing but delta y into delta z. Similarly you can write SW. So now west phase, so normal obviously in the negative x direction, so you can write minus AE I, okay, and it will be minus delta y into delta z I, okay. So we are considering orthogonal Cartesian mesh, okay. So obviously the magnitude of the surface area vector AE is equal to the AW, which is your magnitude of the surface vector of west face. Similarly SN, okay, you can write A north, okay, and in j direction, so it is the unit normal in the j direction. So you can write, so now AN, so this face, okay, right face, so it will be delta x into delta z. So it is delta x into delta z into j. Similarly SS, okay, south face, so it will be minus ANJ and it will be minus delta x delta z into j. And similarly now for the top surface vector, so that this one on the top, so you can see this is of surface area delta x into delta y. So it will be A top, so now unit vector in that direction is k, so it will be delta x into delta y into k. And similarly bottom, so unit vector in negative z direction, so A bottom, sorry, this is you can write AW, SW, and this is your A south, okay, although in this particular case it is same, and A bottom k is equal to minus delta x delta y k. And you can see that for this particular case we are considering infinite volume method. So generally we use the cell center as P and the neighbors as east, west, north, south, top and bottom. So the compass notation we can compare with the finite difference method as, so P is the main control volume, so this is your I, j and k, okay. So similarly east, okay, so it will be in I plus 1 j k, okay, west it will be I minus 1 j k. So these are the indices, okay. So P, so the east cell is just front side, that is your neighbor cell. W, okay, neighbor cell in the west side. So how many neighbors will be there? For this 3-dimensional case, it will, there will be 6 neighbors, because 6 faces are there, so 6 neighbors will be there. So now north, so it will be I j plus 1 k, south, so it will be I j minus 1 k, then now top bottom, so top will be just I j k plus 1 and bottom as I j k minus 1, okay. So in finite volume method generally we write the discretized equation in 2 dimension up to south. So P is the main control volume, then east, west, north and south, and if it is 3D then top bottom will come. As we told that in finite volume method we use the integral form of the governing equation, and finite volume method inherently conserves the basic conservation of governing variables. Okay. So, let us see how it does. So, let us consider 1D case. Okay. So, in 1D case you can see capital P is the main control volume, capital E and capital W are the neighbors cells, and delta x is the distance, and small e and small w are the phase center. Okay. So, it is 1D case. Okay. So, now let us write the steady convective diffusive equation. So, for general variable phi. So, what is that? So, it will be divergence of rho u phi, okay, is equal to divergence of gamma grad phi plus some source term s phi. Okay. So, now you can rewrite it as divergence of rho u phi. If you take this diffusion term in the left hand side, then it will be minus gamma grad phi is equal to s phi, and this term will just denote as flux vector j, okay, is equal to s phi. So, flux vector j is your rho u phi minus gamma grad phi. Okay. So, this is the governing equation. Now, we need to integrate over this main control volume P. So, if you do that, so it will be volume integral divergence of j dV is equal to volume integral s phi dV. Now, in the left hand side, the volume integral in divergence form we have written. So, you can use Gauss divergence theorem and convert it into surface integral. So, using Gauss divergence theorem, okay, we will convert this volume integral to surface integral. J dot ds is equal to volume integral s phi dV. So, you can see this j dot ds, now it is surface integral. So, we have two surfaces in 1D, east and west. So, we need to find or integrate this flux vector along these surfaces, okay, east and west in one dimensional case. So, now you can see that if you see that each this small e, what is this phase, it is shared by P and E. Okay. So, the flux for P there will be one flux, and for small e also at the east phase there will be flux, but you can see that the outward normal are opposite. So, for small p it is in the positive x direction, and for capital E for the phase small e the outward normal is negative x direction. The same flux you are calculating at the east phase, but they are opposite in sign. So, if you sum up the fluxes in all the phases, then what will happen, at the interior phases all will get cancelled, because you have positive and negative and all fluxes will get cancelled. Only you will be left with inlet and outlet fluxes, okay, and hence it conserves the conservation variable. So, if we sum up all the fluxes at the phases, we can see that it will depend on inlet and outlet boundary. as fluxes will cancel out at interior faces. So, now you can see in this equation. Okay. So, now up to this we have not done any assumptions, okay. Just we have integrated over this, but you can see that when you are integrating this at the east face, okay. So, we will consider the average value of this flux J at the phase center small e, and we will write as J E dot AC, okay. And here we will write plus J W dot S W, okay, is equal to, now this volume integral whatever we have, we will consider one average value, and using mean value approximation we will write S phi at the cell center P into V. V is the volume of this cell, okay. Volume of this cell is V, okay. So, now you can see that we have approximated this flux vector, this integral, we have approximated this flux at the phase center value, okay, and this S phi we have taken the average value at the cell center S phi P using mean value approximation. And whatever this mean value approximation we have taken, now we will show that these are second order accurate, okay. These are second order accurate, and it is second order accurate for any arbitrary control volume and non-uniform mesh, okay. Now, we will find the order of accuracy of this mean value approximation. Mean value approximation. Again we will consider 1D cell. So, P is the main cell center, capital E and capital W are the neighbor cell center, small e is the east phase center and small w is the west phase center, and delta x is the main control volume. It is actually delta x into 1, this is the volume of this cell, and you can see that small e and small w will be located at a distance delta x by 2 from the main cell center, because P is located at the center of this main control volume. So, the distance between small e and small p will be delta x by 2, and the W and P, the distance will be delta x by 2. So, now if we consider the control volume V as this one, okay, and in this case it is delta x, and we will consider any function phi x, okay, in this control volume, okay, consider the function phi x in the control volume. So, now you expand this phi x, okay. So, we will consider, so here one point which is x, okay, distance, and the p is at x p distance, okay. From the left hand side, the left boundary, the distance of p center is x p, and this is your x. So, now we can consider using Taylor series, okay. We will write the phi x as phi p, okay. About the phi p we are expanding. So, x minus x p, so this is your delta x d phi by dx, okay, at p plus x minus x p whole square by factorial 2 d 2 phi by dx square, okay, and plus x minus x p whole cube by factorial 3 d cube phi by dx cube, and order of approximation is delta x to the power 4. So, if you neglect the other higher order terms, then it will be order of delta x to the power 4. So, now let us integrate this function in this control volume. So, now as it is 1D, we will write x w to x e, okay, phi x dx. So, what we can write now? So, phi p is the just the value of phi. So, it is a discrete value. So, you can take it outside the integral. So, it will be x w to x e dx, okay, plus now you can see d phi by dx. Okay. So, this is your pointwise values. So, it can be taken outside the integral, because d phi by dx at p you will calculate. Okay. So, you can take it outside the integral. Okay. It is as pointwise values. So, you can write d phi by dx, okay, at p integral x w to x e x minus x p dx. Similarly, d 2 phi by dx square you can take it outside, d 2 phi by dx square at p x w to x e x minus x p whole square into dx, and we can have the order of approximation, okay, or you can write another term. So, d cube phi by dx cube, okay, at p x w to x e, sorry, here it will be factorial 2. So, divided by factorial 2, and this will be x minus x p whole cube by factorial 3 d cube phi, d cube phi we have written, plus order of delta x to the power 4. So, now you if you integrate it, so what you will get? So, you can write x w to x e phi x dx. Okay. So, you can see if you integrate this dx, so it will be x w minus x e. So, what is that? So, if you integrate it, you will get x e minus x w. So, x e minus x w. So, you can see x e minus x w is nothing but delta x. Okay. So, you can write phi p into delta x plus, okay. Now, if you integrate it, so it will be x minus x p whole square by 2, and if you put the limit, then you can write d phi by dx at p. So, you can write as, so half, okay, x e minus x p whole square minus x w minus x p whole square, okay. Then you can write this one. So, 1 by 6 d 2 phi by dx square at p, okay. 1 by 6 you can write 1 by 6. Now, you can write x e minus x p. So, if you are integrating, so it will be cube minus x w minus x p cube, okay, d 2 phi by dx square. Oh, you have written this. So, you do not need to write, okay. And you can write, okay. So, if you neglect the other terms, so it will be order of delta x to the power 4, okay, order of delta x to the power 4. So, now you can see, okay, the x e minus x p, what is the value? X e minus x p is the delta x by 2, and x w minus x p, it is minus delta x by 2. So, if you see the distance between this x c and x p, what we are writing here. So, x c minus x p is delta x by 2, okay. This is the delta x by 2, and x w minus x p okay, x w minus x p. So, it will be obviously minus delta x by 2, because from p it is going in this direction. So, it will be minus delta x by 2. So, now if you put it here, so you can see this is squared. So, delta x square by 4 and minus this is also delta x square by 4. So, it will become 0. So, second term will become 0, but the third term will not become 0. Okay. So, you can write it as x w to x e phi x dx is equal to phi p delta x. So, this term is getting 0, okay. And here if you see, so it is delta x cube by 8, right. So, it is factorial 2. So, this is your factorial 2. So, it will be 2 into 3, okay. So, it will be 6 and 6 into 8, okay. So, it will be d2 phi by dx square at p. So, now you can see this is your delta x cube by 8 and this is minus minus plus. So, this will be delta x cube by 8, okay. So, it will be 2. So, these two terms will be 2 delta x cube by 8, that means delta x cube by 4. So, and 4 into 6. So, it will be 1 by 24 delta x cube, okay, plus order of delta x to the power 4. Now, you see. So, now if you approximate this integral and if you take only the first term, then you can write phi p into delta x and you can neglect the other terms. So, what you can write? So, phi p, which is your average value at the phase center, okay, of this function phi x, you can write 1 by delta x x w to x e phi x dx, okay. So, this if you write, then you can write it as phi p, okay, plus delta x you are dividing. So, it will be order of delta x square. So, whatever function you are integrating in the main control volume or whatever function you are integrating over the main control volume, and if you take the average value at the cell center, then you can see that it is second order accurate, okay. So, that we have proved, and it is true for non-uniform grid as well and any arbitrary control volume, okay. We have shown it for one dimensional grid, but you can show it for any arbitrary control volume that the mean value at the cell center if you take, then that will be second order accurate. And we can write in general phi p is equal to 1 by b, it is the main control volume p. So, volume integral phi dv as phi p, which is your second order accurate, okay. And in the next lectures we will see that we will discretize this convection diffusion equation and we will use this mean value approximation, and you can see that it is second order accurate. So, whatever we have shown, so that is true for any source term as well, because the source term we are integrating over the main control volume and the average value we are taking at the cell center. So, that will be your second order accurate. So, the S phi, okay, at p, which is if you are integrating over this control volume, then you can write 1 by v S phi dv, okay, over the volume, and it will be S phi p, and it is also second order accurate, okay. This is also second order accurate. Okay. It is also true for the phase integral. So, any quantity which you are integrating over the phases, and if you take the average value at the phase center, so using this mean value approximation you can show that this is also second order accurate. So, whatever these fluxes we are integrating over the phase, okay, J E or J F, So, that if you take the average value at the phase center, so that will be second order accurate. So, JF, okay. So, the same analysis can be applied to the phase flux. Okay, so, JF you can write as phase flux JF. So, phase flux JF. So, you can write integral phases JF dot ds, whatever we are doing. So, that we can write as JF dot SF, which is your second order accurate, okay, using mean value approximation. And also the mean value approximation is order of delta x square, second order accurate, okay, even for non uniform grid. Okay. And the approximation is independent of of the control volume, shape, and it is applicable to 2 and 3 dimensions. So, this was found to be good compromise between accuracy and flexibility while keeping the method simple and relatively for low computational cost. So, now if you see the flux vector, we have convection flux as well as diffusion flux. So, if you consider the diffusion flux only, then there will be a gradient, okay. So, at the phase center. So, to calculate the gradient at the phase center, so we will see what is the accuracy of this discretization. So, this is your gradient approximation. Okay. So, let us consider only diffusion flux. So, whatever the integration we have done, the flux vector contains convective flux and the diffusive flux, but now let us consider the diffusion flux only. So, J for diffusion flux if you consider, it will be minus gamma grad phi. So, if you write the JE dot AC, okay, so the flux vector diffusion flux vector dot the AC. So, at this east phase we are calculating this JE dot AC. So, what you can write minus gamma grad phi at east phase dot AC, okay, and AC is nothing but AE into I, okay, and grad phi, okay, if you see it will be del phi by del x I plus del phi by del y j. So, you can write it as minus gamma E AE del phi by del x at E. So, you can see we need to calculate this del phi by del x at the east phase center. So, to calculate that we will use Taylor's series again. Okay. So, you can write phi E, okay, if you expand it, okay, about small phi E. So, it will be phi E plus delta x by 2 d phi by dx, okay, at E plus delta x square by 8, okay, d2 phi by. So, here you can write d phi by dx because you are considering only one dimension. So, d2 phi by dx square at east, okay, plus delta x cube by 48 d cube phi by dx cube, okay, at east and other higher order term. Okay. Similarly, phi p you can expand about small e. So, it will be phi e minus delta x by 2. So, delta x by 2 is the distance from small e to small p. So, you can write d phi by dx east plus delta x square by 8 d2 phi by dx square at east minus delta x cube by 48 d cube phi by dx cube at east plus order of delta x to the power 4. Okay. So, now if we tell that this is your A and this is your B. Okay. So, now subtract the second equation, subtract equation B, okay, from equation A. So, what you will get? So, if you subtract, you can see that this term will get cancelled, the other terms will get cancelled. So, you will get d phi by dx, okay, at east will be phi e minus phi p divided by delta x plus order of delta x square. Okay. So, you can see the assumptions that if phi varies linearly between grid points, then it will lead to truncation error of delta x square. Okay. But it is true for only for uniform grid. So, if you use uniform grid, then the gradient at the phase center, if you calculate, then you will get second order accurate, but non-uniform grid you will get the order of accuracy as delta x. Okay. So, today we have started with the terminology of these finite volume cells, then we introduce the volume and area, okay, for 2D and 3D finite volume cells. Then we have used steady convective diffusive equation, and introducing the flux vector we integrated the governing equation in the main control volume P, and we have written in the surface integral form of this flux vector. And when we integrated the source term, okay, we have used the average value of the cell center. Now, this approximation depends on this mean value approximation. So, using this mean value approximation, we have shown that if you use the average value at the cell center, then it gives second order accuracy even for arbitrary control volume or non-uniform grid. Same thing is also applicable when you are using the surface integral and taking the average value at the phase center, and that is also we have discussed the flux vector when you are integrating over the phases, then the average value at the phase center whatever we have taken, that is second order accurate. While discretizing the diffusion flux vector, the gradient of phi at the phase center it will come, and if we use uniform grid, then if we take the difference between the neighbor values divided by the distance between those cells, then that gradient will be second order accurate. But if you use non-uniform grid, then it will be no longer second order accurate, it will be first order accurate. So, in the next few classes we will consider steady diffusion equation, then unsteady diffusion equation and convective diffusive equation, and we will discretize using this finite volume method, and we will use this mean value approximation. Thank you.